in a coarse mode, size distribution, complex refractive index, a fraction of non-spherical aerosols, and then also retrievals of some properties over land. This algorithm works over land, this algorithm works over water. So that's sort of what you can do with Polar. Now, I mentioned before that Polar has this 2% uncertainty value. So there was an effort to try to break this down, and this was NASA's effort. This was an instrument called the Aerosol Polarimetry Sensor on Glory. Compared to Polar, this was supposed to have many viewing angles, 250 instead of 16, roughly an order of magnitude more accuracy in terms of polarization. The consequence of all this is that this, unlike Polar, which has a wide swath and makes global measurements, is a single pixel wide instrument. So this is not something that we would make nice pretty maps with, but would be useful for the purposes of aggregating statistics globally about aerosol properties. And the idea is that we have all this information so we can do a good retrieval in a smaller portion of the globe. But if it's a uniform sampling, this is useful. This also uses a retrieval algorithm that was developed at NASA GISS. The problem is that Glory did not reach orbit. The spacecraft crashed, and this is the nature of the business we are in. So NASA has not rebuilt the instrument, so at the moment there isn't plans to build a Glory-like instrument for space. Okay, so that's it. That's a short list of what's in orbit. And as you notice, I mentioned Polar is no longer in orbit, so we're at this state where we have reduced capability than we did a couple of years ago. Of course, there's many things in the works, and a lot of work is being done right now with airborne prototypes, so I'll go through a couple of these. RSP is the prototype of the instrument that was on Glory, the APS instrument. This has had 15 plus years of field deployment. There's actually 2 of them, and they go in everything from these low altitude planes that do profiles to these high altitude planes like the ER2 here, which is as close as you can get from an aircraft to a simulation of the satellite. So just as a reiteration again of what the RSP is like, it's a single pixel wide scanning instrument, first 3 elements of the Stokes vector, these channels, and a high polarimetric accuracy. Another instrument, and this uses Wolfson prisms, like I said before, to split the beam into polarimetric components. Another instrument which is being developed, or which has been developed at the Jet Propulsion Laboratory, is called AirMISPI. This is the Airborne Multi-Angle Spectropolarimetric Imager. A lot of these people in this group are the same as the MISR mission, which I mentioned way back before, the multi-angle instrument. This uses what's interesting about this instrument is that there is a CubeSat version, a small satellite version, which possibly will be launched in early 2013. So there may be another polarimeter in space soon if this works. Another approach is called SPECS. This is spectropolarimeter for planetary exploration, and this uses yet another method of beam sensitive polarization. Here they have a hyperspectral measurement, and they impose onto that spectra sort of a sinusoid which contains information about the polarimetric state. They do this using quarter wave retarders. And this is an instrument developed in the Netherlands, but they're very interested in working with NASA. So they're actually integrating this instrument on the high altitude aircraft that I mentioned before. Okay, so that's sort of where we are in the state. There's a number of other airborne instruments. What I described here are really what's relevant within North America and the measurements that are likely to be made in North America. The French have a couple of polarimeters. I know of at least 2 that exist in China. But this is what's I'm most familiar with, at So there's all these different polarimeters that exist. The question is, what are we going to build in the future? What choices do we make between all these different characteristics between these instruments? And as part of that, I have I guess, a responsibility in that I moderate a working group. It's called a polarimeter working group for a NASA mission called ACE. And coincidentally, this group had its monthly teleconference last Friday. So when Rajan sent out that email about, really focus on what the current issues are, I brought it up as a topic of conversation. So I came up with a list of things that my little subcommunity thinks is important for polarimetric reminiscence and aerosols. And so that's what I'll show here. So there's essentially three different categories of things that are important. One of them is instrument design, calibration, and configuration. How do you build a system like this? The next is algorithm development and data exploration. How do you exploit the data that comes from one of these instruments? And finally, how do you validate the data, and how do you actually use the data for improving climate models? And I think, to be risk averse here, I should say that all of these opinions are my own, and they do not represent NASA or the ACE Polarimeter Working Group. Okay, so first thing, instrument design, instrument calibration, and configuration. Well, the first thing is that, as I mentioned before, we are in a state of post-polar where we face reduced orbital data capability. So the question is, we should launch something. Easier said than done. There are some missions in the works. Two of them from NASA are ACE. The ACE is a decadal survey recommended mission. ACE will have a polarimeter and two other types of instruments on it. It doesn't have a fixed launch date, or it's not even really fixed what the characteristics of the polarimeter on it should be. In fact, a lot of the reason that we're doing all these airborne campaigns is as a testing of a bake-off of different polarimeters with potential implications for ACE. A more near-term instrument is called PACE, sort of uncreatively named the pre-ACE mission. But there is this is aerosol cloud ecosystems. This is aerosol cloud and ocean ecosystems. So really the primary focus of PACE is ocean color measurements. And if you're trying to make measurements of optical properties of the ocean, of chlorofyll concentration, and so on and so forth, you have to realize that maybe 10, 15, 20% of your signal are interactions that occurred in the body of water. The rest happen in the atmosphere. So this community needs to get very serious, or is very serious, about its atmospheric correction. A lot of that uncertainty is in how they resolve the aerosols. So the original plan of PACE is to take some sort of standard ocean color instruments that exist, add wavelengths, move them into the UV, and try to improve the atmospheric correction by putting a polarimeter on board. The first thought, and the first plan with PACE, was to put the successor to Polder, which is called 3MI, as a contributed French instrument onto the PACE mission. But that hasn't come to play. So, so there's some decisions that are happening in the next couple of months as to, do we build an instrument? What instrument do we build? Do we solicit a contributed instrument from another country? It's a little uncertain with PACE right now. And there isn't a lot of money to build a polarimeter. The original plan of this mission was to have a contributed mission from another country. So part of this is what's the optimal instrument design? Maybe I'll skip over this and say that there are Bayesian information theory techniques that allow you to do things like this. Say, okay, if we had some perfect world with a perfect retrieval algorithm where we can converge to a solution, what, with these different types of instruments, could we expect to see in terms of this is uncertainty? Of these different components, things that you want to retrieve. So this is saying, all right, with the x-axis is aerosol optical depth. So we could see that, say, as we have more aerosols, our uncertainty in retrieving the effective radius of the fine mode of aerosols gets better. Polarimetric calibration and characterization is important. This is a polarization state generator that is being used, but needless to say that the maturity of characterization of polarimetric instruments is not at the level of radiometric instruments, and I think I'm probably running out of time here. Data management's an issue. I have more slides of this. So this is from an instrument design, from a data development and data exploration design. There's many things that we need to understand. I asked a question earlier today about, what are the models that we should use to describe our aerosols? We want to think in terms of complex refractive index. What properties should we use? What parameterization choices can we make? How do we account for clouds? Clouds can play a confounding role, as can 3D scattering, as can the vertical distribution of aerosols, surface reflectance of the models, and so forth. These are all things that we need to design a retrieval model that successfully handles all of these things. This is an effort to compare retrieval polarized radiative transfer algorithms. Okay, I'll just go with that. And then finally, how do we apply this data appropriately? One of the things is, how do we validate our complex refractive indices from the ground? And I think a lot of people here are making measurements that are appropriate for that. But we need to be talking the same language in terms of validation. And then we also need to be talking the same language with the modelers. How do we take our retrieve values and say something relevant to the modeling community? So one approach, for example, is to make climate models have remote sensing products, which is kind of nice. So that's it. So these are the people that were a part of that teleconference when I discussed some of the issues. They gave a lot of their opinions here. And I just want to say that this is an image from the ER2 aircraft that I mentioned before, which really does look like it's in space. Thank you.